Hello, everyone, and welcome back. So we're looking at exponential and logarithmic functions, and in this video, we want to talk about logarithmic functions. So over here, what is a logarithmic function? Well, a logarithmic function is defined as um, y is equal to log base b. Okay, so this bottom one is called the base. This is log base b of x, and there are some conditions on these variables. X has to be positive. You can't take a log of a negative number, and x is an element of all real numbers. B also has to be positive. Your base cannot be a negative number, and it also cannot be 1, or else you'll have an undefined function. So let's understand a little bit of this. So y is equal to log base b. Over here, we say that the value of the logarithm is basically y. You're saying y is equal to this log, and so that's the value of the logarithm. And over here, the base is the base of the logarithm, and that's your b, and x is the argument. So you're saying log of something, okay? All right, so a logarithmic function is the inverse of the exponential function. And so what that means is that, remember when we said inverse functions, it's basically replacing x and y and then solving for your y value. That's basically what happens over here. So if I say the inverse of an exponential function, for instance, with base 2, so let's go y is equal to 2 to the power of x, that's my exponential function, okay? And then if I have my logarithmic function, which I'm saying is going to be the inverse function, okay, log function. So I'm going to have y is equal to log base 2. So I have that same base, okay? Log base 2 of x. Now, if I were to graph this, they'd, right, if I were to graph this function over here, it should give me the same exact function as graphing x to the power of 2y, okay? And so if we were to graph both of these functions, this first one and this second one, you'll see that they're inverses of one another, right? And I've already graphed them for us. So if we look at the plot over here, I have 2 to the power of x and log base 2 of x, and the line that that the inverse happens about. So they're reflected about the line y is equal to x. So when I graph them, you can see that y is equal to x is this green one over here, and log base 2 of x is the blue one, and y is equal to 2x is the red one. You can see that they're inverses of one another because they're exact reflections about the line y is equal to x, right? So they're inverses of one another. And so in general, we write y is equal to log base b. Okay, so this one over here, log base b of x, instead of saying x is equal to 2 to the power of y. Why is that? Is because we never represent a function in terms of x is equal to something. And so if it is represented as x is equal to something, then I need to isolate and solve for y, which ends up giving me this y is equal to log base 2 of x. Okay, so the logarithmic function, as we've understood, there are a few things that I want to highlight about it. So the inside of the logarithm, in this case, we can see it's x. This is what we call the argument, and the argument can never be negative, and that's why x has to be positive, as we see over here. Okay? All right, so let's talk about some characteristics in the logarithmic function. Now, why is it important that we look at these characteristics? Is because whenever you're working with a function, you need to be able to understand key information about it. So the characteristics of the graph of the logarithmic function y is equal to log base b of x. We kind of saw how it looks over here, right? So this blue one is the log base x, right? So you can see that as you can see that we originally had with the exponential, the red one, we had the asymptote x is equal to 0, a horizontal asymptote. Now, because we took the inverse of it basically to get the log function, instead of y is equal to 0 being your horizontal asymptote, now you have a vertical asymptote, y is equal to 0 instead of x is equal to 0. Okay. All right, so let's go back here. So over here, you have the x-intercept is 1. Okay, so this is the key thing over here. Your x-intercept is always going to be 1. All right, regardless of what you do, what b is, what x is, you're always going to have the x-intercept of 1. And so anytime you're drawing your parent function, you're always going to have that main point 1 and 0. So your x-intercept is 1. There are no y-intercepts. Remember with the exponential function, we had over here, there are no x-intercepts, right? There are no x-intercepts. In this case, there are no y-intercepts, right? Because we're looking at logarithmic functions. So they're inverses. And so over here, the y-axis is the vertical asymptote with the equation x is equal to 0, right? So we talked about this before. Over here, we're going to have the horizontal asymptote, the vertical asymptote, y is equal to 0. And then the domain we can see is just going to be x is an element of all real numbers such that x is greater than 0, right? Because like we saw, it's going to be, it's changing with the exponential function because we're taking the inverse and look at exponential function. The range was the one where y was greater than 0. And again, we can see that they're going to switch. So that's going to be the domain, and the range is going to be y is an element of all real numbers. Because if we look at the graph of the logarithmic function, it looks something like this, right? So here's our y-axis, here's our x-axis, here's our y. It looks like this, all right? So here's its intersection, its main one, 1 and 0. So it's x-intercept. And then this one approaches 0, so I'm going to draw it a little bit more approaching 0. So kind of like that. Okay, so if this continues on like this, you can see that it approaches 0. And so why you have this, or this vertical asymptote x is equal to 0, right? Where your logarithmic function is going to be approaching, but it's never going to touch. Okay, so that's why you can see that the domain has that restriction of 0 of x being greater than or equal to 0, and the range being all real numbers since it extends in both directions. Okay, and then we can see over here that y is equal to log base x log base b of x is equivalent to x is equal to b to the power of y. We talked about that here. And we know that it has these same restrictions over here where x has to be greater than 0, b has to be greater than 0, and b is an element, b cannot be 1. The base b can, of both logarithmic functions and exponential functions, it is the same base, and we saw that over here as well, where we had a base 2 and base 2 for the same function, okay? And it's also for its inverse, right? So over here, if I were to say, you know, here's the log, here's its inverse, they have the same base b. Okay, now here are some notes that I've included because I thought they were important. So since the logarithmic function y is equal to log base b of x is only defined in the positive values of x, so we can see it's only defined in this direction over here. The logarithm of a negative cannot happen, right? So you know how we said x has to be positive, right? X cannot be negative. This is why, because it's not defined for x is a negative number, okay? Another thing is that the logarithmic equation y is equal to log base b of x can be expressed as the form of x is equal to b as the power of y. We've done that twice so far over here, and we've done it initially over here as well. It is really important to recognize that exponential functions are basically logarithmic functions. So if you're ever the inverse of logarithmic functions. So if you're given something like this, x is equal to 3y, and you're asked to write it as a logarithmic function, you take this is the same base, so you go log base 3 of the other side is equal to y. So you're saying, how can I solve for y, basically, right? Your question is, how can I solve for this y in the exponent? Well, here's how. You take the log of this base of this argument on the other side is equal to your exponent, okay? All right, and this is really important. That's why I've mentioned it several times. And the last one is the exponential equation y is equal to b to the power of x can be expressed as the logarithmic equation log b y is equal to x. Basically, they're telling you that you can go back and forth between them. And so these are two really important points that I wanted to get across. And the last topic here that I want to talk about is really dive into the logarithmic form y is equal to a b of x, right? So we've been looking at the logarithmic y is equal to just b of x, right? Something like this over here, just b of x. Now we're interested in what if I have an a value, right? Now, when you have an a value, then you're just saying, oh, okay, so you're going to write this exponential form y is equal to a b of x. You can rewrite this as y over a is equal to b of x, right? Because I can divide both sides by b of x. And then if I wanted to change this exponential form to a logarithmic form, then again, I'd say log of the same base of the other side, which is my argument, y over a is equal to that exponent x, okay? And so it's the same idea. You're just saying that over here, I take this a to the other side like this, and now this becomes my argument, and I go log of base b of this argument, which is the other side, is going to equal to the exponent, okay? All right, now, that's pretty much it, honestly, for the logarithmic functions. We covered everything I wanted to cover, which is understanding what the logarithmic form is, understanding that it's the inverse of the exponential, being able to go from exponential to logarithmic. That's really important, and knowing some characteristics about the graph as well and how the graph looks. Okay. All right, everyone, that's it for this section. Join me in the example videos where we're going to see this in action. Bye.